Welcome to this solution walkthrough. Today, we will tackle LeetCode problem number 956, tallest billboard. In this problem, we'll explore how to split a collection of rods into two groups of equal height, uncovering efficient approaches to solve this interesting challenge. Let's dive in. Imagine you're building a billboard supported by two vertical rods, and you want these supports to be as tall as possible. You have a collection of rods, each with a specific positive length, and your task is to use some of these rods to construct two supports of equal height. Any rods that you don't use can be discarded. The goal is to determine the maximum possible height of the two supports if you can make them equal. If it's not feasible to create two supports of the same height, the result should be 0. The input consists of an array of integers where each value represents the length of a rod. The output is a single integer, representing the maximum height of the two supports, or 0 if it's not achievable. The constraints indicate that the number of rods will be between 1 and 20, and each rod length will range from 1 to 1000. Additionally, the total sum of all rod lengths won't exceed 5000. Let's look at the first example to understand this better. Suppose we have an input array of rods with lengths 1, 2, 3, 6. The output in this case is 6. Here's why: we can use the rod of length 6 to form one support, and for the second support, we combine the rods of lengths 1, 2, and 3, since 1 plus 2 plus 3 equals 6, both supports have the same height. This configuration ensures the maximum possible equal height of the two supports is 6. Now, consider another example where the input array is 1, 2, 3, 4, 5, 6. The output in this case is 10. To achieve this, we can construct one support using the rods of lengths 6 and 4, which add up to 10. The second support can be built using the rods of lengths 5, 3, and 2, which also sum to 10. Since both supports reach the same height of 10, this is the maximum achievable equal height for these rods. In contrast, if the input array is 1, 2, the output is 0. This is because it's not possible to divide these two rods into two groups such that the heights are equal. The rods are simply too short and cannot be rearranged to meet the requirements of the problem. This illustrates that not all configurations of rods will allow for two equal height supports to be created. There are a few key edge cases to keep in mind. First, if there is only one rod, it's impossible to create two equal supports, so the result will always be 0. For example, with rods equals 5, the output is 0. Next, if the number of rods is small and no valid configuration exists, the result is again 0, such as with rods equals 1, 2, 3. On the other hand, if all rods have the same length, the solution involves splitting them into two equal groups. For instance, with rods equals 5, 5, 5, 5, the output is 10 because the rods can be split into two groups of 10 each. Another important case is when the total sum of all rods is odd. Here, it's impossible to split them evenly, leading to an output of 0. Finally, with a large number of rods or high values, efficient computation becomes critical due to the constraints on both the number of rods and their total length. To solve this problem, we need to think about the rods as being divided into three groups: those used in the first support, those used in the second support, and those discarded entirely. A dynamic programming approach works well here. The key idea is to track the difference between the heights of the two supports and the maximum achievable height for that difference. This allows us to systematically explore all possible combinations of rods while efficiently arriving at the optimal solution. When approaching the tallest billboard problem, one intuitive method is the brute force approach. Here, the goal is to divide the rods into two groups so that their heights are equal, while maximizing the total height of these groups. To do this, we would generate all possible subsets of rods and examine every valid partition. For each partition, we calculate the difference in heights between the two groups, and if the difference is 0, we track the maximum height achieved. While this approach is simple and easy to understand, it comes with significant drawbacks. Generating all subsets of rods leads to exponential time complexity, specifically O(2 to the power of n), which makes it impractical for larger input sizes. This trade-off between simplicity and performance makes brute force infeasible for solving the problem efficiently. To address the inefficiencies of the brute force method, we turn to an optimized approach using dynamic programming. This technique allows us to track the possible differences between the heights of the two groups without explicitly generating all subsets. The core idea is to maintain a state using a hash map, where the key represents the difference between the two groups, and the value represents the maximum total height of rods used to achieve that difference. The process begins by initializing the DP dictionary with a base case, a difference of 0 and a total height of 0. For each rod, we update the dictionary to account for 3 scenarios: adding the rod to the first group, adding it to the second group, or skipping it entirely. As we iterate, we compute new differences for each existing state and update their maximum heights accordingly. By the end, the value stored at a difference of 0 in the dictionary represents the tallest possible billboard, as it corresponds to 2 groups with equal heights. This approach, while more complex to implement, reduces the time complexity to O and asterisk sum, where sum is the total length of all rods, making it vastly more efficient. The dynamic programming approach works so well because of several key observations. First, the problem can be reframed as finding 2 subsets with equal sums, which allows us to focus on tracking the difference between their sums rather than explicitly dividing the rods. This reframing simplifies the problem and reduces redundant computations. Second, by using a hash map to store only the relevant states, we ensure that the space and time complexity remain manageable. Instead of maintaining a massive set of combinations, we incrementally update achievable differences as we process each rod. These insights form the foundation of the chosen strategy, which is the dynamic programming approach. While the brute force method may seem straightforward, its exponential nature makes it unsuitable for large inputs. In contrast, dynamic programming strikes an effective balance between efficiency and implementability, leveraging the problem structure to focus on achieving the optimal solution. Each approach to solving this problem comes with its own trade-offs. The brute force method, while intuitive, is computationally infeasible for larger inputs due to its exponential time complexity. Dynamic programming, on the other hand, requires more careful implementation but offers a far more efficient solution within the problem's constraints. Greedy or heuristic approaches are not applicable here because the problem demands an exact division of the rods, and these methods cannot guarantee optimality. By choosing the dynamic programming approach, we achieve the best balance between performance and correctness. It allows us to solve the problem efficiently while adhering to the requirements of finding the exact tallest billboard possible. This makes DP the most practical and effective strategy for tackling this challenge. In this problem, we are given a set of rods, and our goal is to divide them into 2 groups such that the total height of both groups is equal, while maximizing this total height. This is a challenging task because it's a variation of the subset sum problem, which is known to be NP-hard. To solve this problem, we need to approach it systematically. First, we can define the problem mathematically. Let's say the rods are represented as an array of heights equals h1, h2, hn. We need to partition these rods into 2 groups such that the sums of their heights, sum 1 and sum 2, are equal. That is, sum 1 equals sum 2. At the same time, we aim to maximize the value of sum 1 or sum 2 since they're equal. This gives us a clear optimization goal and sets the stage for exploring potential solutions. Now, a natural starting point to tackle this problem is to consider a brute force approach. This involves generating all possible subsets of the rod heights and checking for each subset whether the remaining rods, those not included in the subset, form a group with the same total height. If this condition holds, we calculate the value of sum 1 and track the maximum value encountered. However, this approach comes with a significant drawback. Generating all subsets of the array involves exponential time complexity, specifically O(2 to the power of n), which becomes infeasible for larger inputs. To overcome this inefficiency, we can use dynamic programming to optimize the solution. With dynamic programming, we store intermediate results to avoid redundant calculations. Here's how the optimization works. First, we define the state of our DP table. The DP table is represented as DP, I, J, where I refers to the first I rods considered, and J represents the height difference between the 2 groups. The value stored in DP, I, J, is the maximum total height of the shorter group when the height difference between the 2 groups is J. The base case for this table is straightforward. If no rods are considered, the height difference is 0, and the maximum height of the shorter group is also 0. This is captured in DP, 0, 0, equals 0. The next step involves defining the state transitions for our DP table. For each rod in the array, we have 3 main choices. First, we could add the rod to the taller group. In this case, the height difference increases, and the new value in the table at dp, I, j plus heights, I, would be the maximum of its current value and the previous value at dp, I1, j, plus the rod's height. Second, we could add the rod to the shorter group. Here, the height difference decreases, and we update dp, I, j heights, I, with the maximum of its current value and the previous value at dp, I1, j, plus the smaller of the rod's height or the current difference. Third, we could exclude the rod entirely, in which case the value at dp, I, j, remains the same as dp, I1, j. Once we've processed all the rods, the solution to our problem lies in the value of dp, n, 0. This represents the maximum total height of the shorter group when the height difference is 0, meaning both groups are of equal height. To reconstruct the solution and determine which rods belong to each group, we can backtrack through the dp table and trace the decisions made during the computation. There are some key insights that make this approach more efficient and intuitive. First, the use of height difference as a core metric simplifies the problem significantly. By focusing on the difference, we avoid the need to explicitly calculate all possible partitions of the rods. Second, dynamic programming is a powerful tool in this context because it allows us to store and reuse solutions to subproblems, avoiding the exponential explosion of the brute force approach. Third, the symmetry of the problem, where both groups must have equal height, enables us to further optimize by eliminating duplicate states. Additionally, certain edge cases highlight how the algorithm gracefully handles different scenarios. For example, if there's only one rod, no partition is possible, so the result is 0. When all rods have the same height, the entire array can be evenly divided. Lastly, in cases where there are large differences in rod heights, the pruning effect in the dp table allows the solution to converge more quickly, as many impossible states are naturally ignored. The implementation of this approach relies on two key data structures. First, we use a 2D dp array to store the maximum total height of the shorter group for each possible height difference. The dimensions of this array are determined by the number of rods and the maximum possible height difference, ensuring we cover all potential states. Second, a backtracking array can be used to track the decisions made during the dp process, allowing us to reconstruct the two groups of rods. In terms of complexity, the time complexity of this approach is O, n asterisk max underscore diff, where n is the number of rods and max underscore diff is the maximum possible height difference. This is a significant improvement over the exponential complexity of the brute force approach. The space complexity is also O, n asterisk max underscore diff, due to the dp table. Overall, this optimized algorithm strikes a balance between efficiency and clarity, making it a practical solution to an otherwise computationally challenging problem. This implementation solves the tallest billboard problem using dynamic programming with a dictionary to track differences between two groups of rods. The dp dictionary maps differences, keys, to the maximum possible height of the smaller group, values. Initially, the dictionary starts with only one entry, 0, 0, which means no difference and no height. The algorithm iterates through each rod in the input list. For each rod, it computes two scenarios for every current state in dp, adding the rod to one side of the billboard or the other. When adding the rod to one side, the difference increases, and when adding to the other, the difference decreases. The dp dictionary is updated to ensure the maximum height is recorded for each difference. The key insight is that when diff equals 0, the maximum height stored in dp, 0, represents the tallest billboard with equal heights on both sides. By the end of processing all rods, dp, 0, contains the result. This approach is efficient because it avoids recalculating states by reusing results stored in the dp dictionary. The solution has a time complexity proportional to the product of the number of rods and the range of possible sums, making it feasible for the problem's constraints. This is the Java implementation of the tallest billboard problem. It mirrors the logic from the Python solution by using a hash map to track the difference between the two groups and their corresponding maximum heights. Key differences include Java-specific type declarations, the use of the hash map class instead of Python dictionaries, and Java's method calls such as put and get or default. The code is optimized to handle the problem efficiently and is structured as a complete class definition for direct use on LeetCode. To solve the problem, we start with the given rods array, rods equals 1, 2, 3, 6. The first step is to initialize our dynamic programming map, dp, with 0, 0. This indicates that with a height difference of 0, the maximum achievable height on either side is also 0. Next, we process the first rod, which has a length of 1. We copy the current state of dp into a temporary map, current_dp, which starts as 0, 0. For each difference in height pair in current_dp, we evaluate two scenarios, adding the rod to one side or the other. When we add the rod to one side, the new difference becomes 0 plus 1 equals 1, and we update dp, 1, to be the maximum of its current value or the height achieved, which is 1. Similarly, when we add the rod to the other side, the difference becomes abs, 0 to 1 equals 1, but this case doesn't require further updates since it's already handled. After processing this rod, dp is updated to 0, 0, 1, 1. Now, we move on to the second rod, which has a length of 2. Again, we copy the current state of dp into current_dp, which is now 0, 0, 1, 1. For diff equals 0 and height equals 0, adding the rod to one side results in a new difference of 0 plus 2 equals 2, so we update dp, 2, to 2. Adding it to the other side gives a difference of abs, 0 to 2 equals 2, but no further update is needed as the height remains the same. For diff equals 1 and height equals 1, adding the rod to one side leads to a difference of 1 plus 2 equals 3, updating dp, 3, to 3. Adding to the other side gives abs, 1 to 2, equals 1, and we update dp, 1, to the maximum height of 2. After processing the second rod, dp becomes 0, 0, 1, 2, 2, 2, 3, 3. Repeating this process for the third rod, which has a length of 3, we iterate over all values in current_dp and update the dp map accordingly. After processing, dp becomes 0, 3, 1, 2, 2, 3, 3, 6, 4, 3, 5, 6. Finally, processing the fourth rod, which has a length of 6, results in an updated dp map, 0, 6, 1, 5, 2, 6, 3, 6, 4, 6, 5, 6, 6, 6, 7, 6, 8, 6, 9, 6. The maximum possible height of balanced billboards is stored at dp, 0, which is 6. In this example, we use the rods array rods equals 1, 2, 3, 4, 5. We start by initializing dp as 0, 0. As we process each rod, the dp map is updated iteratively. After processing the first rod with a length of 1, dp becomes 0, 0, 1, 1. Adding the second rod results in dp equals 0, 0, 1, 1, 2, 2, 3, 3. When the third rod, with a length of 3, is processed, the map updates to 0, 3, 1, 2, 2, 3, 3, 6, 4, 3, 5, 6. Continuing with the fourth rod, which has a length of 4, the dp map evolves to 0, 6, 1, 5, 2, 6, 3, 6, 4, 6, 5, 6, 6, 6, 7, 6, 8, 6, 9, 6. Finally, after processing the fifth rod, the map becomes 0, 9, 1, 8, 2, 9, 3, 9, 4, 9, 5, 9, 6, 9, 7, 9, 8, 9, 9, 9, 10, 9. The maximum height of balanced billboards is therefore dp, 0, equals 9. In this example, we use the rods array rods equals 1, 1, 2, 2. As before, we initialize dp as 0, 0. Processing the first rod gives dp equals 0, 0, 1, 1. Adding the second rod, which also has a length of 1, updates the map to 0, 1, 1, 1, 2, 2. For the third rod, with a length of 2, the map becomes 0, 3, 1, 2, 2, 3, 3, 4. Finally, processing the fourth rod, which also has a length of 2, results in the final dp map 0, 4, 1, 3, 2, 4, 3, 4, 4, 4. The maximum achievable height of balanced billboards in this case is dp, 0, equals 4. The time complexity of this solution is driven by how many times we iterate over the input and the size of the dp dictionary. First, the outer loop runs once for each rod in the input list. If there are n rods, this loop executes n times. Within this outer loop, we create a copy of the current dp dictionary and iterate over all its key value pairs. The size of the dp dictionary is proportional to the range of possible values for the difference diff, which spans from some rods to some rods. This gives us a maximum size of 2 sum rods plus 1 for dp. For each key value pair in dp, we perform 2 constant time update operations, one for adding the rod to one side and another for subtracting it to form a new difference. These updates take constant time, meaning the work per key value pair is O1. Now, combining all these factors, the total time complexity arises as follows. The outer loop contributes O(n), while the inner loop iterates over all keys in dp, which can be O2 sum rods plus 1. Multiplying these gives the total time complexity as O(n*2 sum rods plus 1, which simplifies to O(n*) sum rods. Shifting our focus to space complexity, it is determined by the size of the dp dictionary. Since dp stores all potential differences diff as keys, with a maximum of 2 sum rods plus 1 keys, the space usage is proportional to O sum rods. Additionally, when we make a copy of dp in each iteration, the memory usage temporarily doubles, but this is still proportional to the size of dp. Therefore, the total space complexity also simplifies to O sum rods. The time and space complexities remain the same across best, average, and worst-case scenarios. This is because the algorithm processes all rods and all possible differences regardless of the specific values in the input. Comparing this to the brute force approach, a naive method would involve generating all possible subsets of rods for both sides of the billboard and calculating their sums to find the tallest configuration. This approach has a time complexity of O2 to the power of n, due to the exponential number of subsets, which becomes infeasible for large inputs. In contrast, the dynamic programming solution significantly reduces this to O(n*) sum rods, leveraging the dp dictionary to reuse previously computed results and avoid redundant calculations. This optimization makes the solution much more efficient, especially for larger inputs, as long as the sum of the rods doesn't grow excessively large. Finally, let's solidify the analysis with a mathematical proof for the time complexity. The maximum size of the dp dictionary is proportional to sum rods, because it depends on the range of possible differences. Since the outer loop runs n times, and during each iteration, we process all keys in dp, the total time complexity becomes O(n*) sum rods. This demonstrates that the dynamic programming solution is far superior to the brute force approach, offering a well-defined polynomial time and space complexity. In conclusion, this method balances computational efficiency with manageable memory usage, making it a practical solution for the tallest billboard problem. When solving the tallest billboard problem, there are a few common mistakes to watch out for. First, not accounting for negative heights can lead to miscalculations. It's easy to assume that all rods have positive heights, but the inclusion of negative values can offset positive ones, which directly impacts the balancing of the two groups. To address this, ensure your solution handles negative numbers appropriately. Another mistake is relying on brute force for larger inputs. While trying all combinations of dividing rods into two groups might seem straightforward, it quickly becomes infeasible due to its exponential complexity, 2 to the power of n. Instead, dynamic programming should be used to optimize performance. Finally, some solutions ignore the requirement that the two groups must have equal heights. Maximizing the total height is important, but it's critical to also verify that the groups are perfectly balanced. A robust solution must check both conditions to avoid failure in satisfying the problem's requirements. Now, let's consider a few more pitfalls. Overlooking edge cases is another frequent issue. Scenarios like an empty array, all rods being the same height, or having only a single rod might seem trivial, but they can lead to runtime errors or incorrect results if not handled carefully. To prevent this, always test your solution against a wide variety of edge cases. Another challenge arises with improperly defined dynamic programming states. If the DP state doesn't capture all relevant factors, such as the difference between the two groups, transitions between states may be incorrect, causing suboptimal results. To address this, take extra care to define the DP state and its transitions in a way that fully encapsulates the problem's requirements. From an interview perspective, this problem offers valuable insights. Recognizing that the tallest billboard problem is a variation of the partition problem can be a game changer. It's often tied to subset sums or differences, so identifying this pattern early helps frame the optimal solution. Interviewers are also likely to evaluate your ability to design an efficient dynamic programming approach, so be prepared to explain your DP state and transitions in detail. Additionally, handling edge cases effectively is crucial, as interviewers often test your ability to manage atypical inputs. Make it a habit to clarify edge cases with the interviewer before starting your code. Lastly, be ready to discuss trade-offs, particularly between time and space complexity. This is especially important when working with DP-based solutions that can be resource-intensive. To deepen your understanding, it's helpful to study related problems. Problem 1049, Last Stone Wait 2, focuses on minimizing the difference between two groups, which is conceptually similar. Problem 416, Partition equals subset sum, involves dividing an array into two subsets with equal sums, a direct parallel to the balancing requirement here. Problem 494, Target sum, is another related problem centered around partitioning subsets to achieve a target difference. Lastly, Problem 879, Profitable Schemes, provides additional practice with subset selection under constraints, making it a good exercise for refining dynamic programming state design. Beyond these, alternative approaches can also be explored. A greedy method, for instance, might involve balancing the two groups in a straightforward way. However, while this can work for small or structured inputs, it doesn't guarantee optimality and often fails for edge cases. Another option is using subset sum with bit masking, which efficiently explores all subsets. While still exponential in complexity, this method performs better for smaller inputs. Finally, the dynamic programming approach stands out as the optimal solution for this problem. By using a DP table to track possible height differences and maximize the total height, you can handle larger inputs efficiently. However, the trade-off is that this method requires careful state design and thorough debugging. Defining the DP state to capture all relevant conditions, like the difference between the two groups, and ensuring the transitions are accurate is critical to achieving the correct solution. With a well-structured DP approach, you can solve the problem effectively while meeting its constraints. Great job! In this walkthrough, we explored how to solve the tallest billboard problem using dynamic programming. Remember, understanding the problem and breaking it into smaller parts is key. Thanks for watching, and don't forget to like, subscribe, and share for more content like this. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!